All right. Hi, guys. Good afternoon. My name is Almog. I work for PLNOG Technologies. My responsibility within PLNOG is focused on switches, primarily on the Ethernet ring. I cover the entire switch portfolio within the company from a products perspective, product management's perspective. Actually, I was not set to present to you guys today. There was another guy supposed to present, and I was asked to fill in for him. So I flew in this morning. I didn't get a lot of sleep, but happy that I'm having the option to talk to you guys. I'm going to talk about. Come on in, guys. Could you sit on this side, please, so we can all be kind of a one group. I'm going to talk about, as the title says, Open Ethernet and overlay networks and how all of this relates to the cloud. Now, I'm sure that all of you know what a cloud is. I was just explaining this to my son the other day, so I'm sure that all of you know what a cloud means. I'm pretty sure as well that all of you know what the overlay network essentially comes to solve and why is it for. I'm going to touch this just a little bit so we will all be on the same page, and then eventually, what is Open Ethernet anyway? So I was at the lecture once by the founder or the inceptor of Ethernet, Bob Metcalf, and he said, well, out of 5 principles of Ethernet, he said one of the top 5 was Ethernet is anything but open. So what is Open Ethernet? And I'm going to touch this later on today. A clicker, that's what I'm looking for. All right. Yeah, it's working. So starting from left to right, this is how traditional networks used to being built. Start with, it was a layer 2 domain with all of the insights or attributes or caveats of a spanning tree. 50% of the network at max could be utilized. A large broadcast domain, that's never a good thing. And then it evolved. It evolved with coming up of MLAG, and then you have 2 aggregation switches. Both are active, so you don't lose 50% of your network. And still, you're also limited to the size of this aggregation switch. And this is also what prompted up large chassis-based devices with a few tens at the beginning and then several hundreds of interfaces. Again, at the beginning, it was 10 gig and then evolved into 40 gig. Now we see that at the 100 gig still. A couple of hundred interfaces, 300, 400, 500, this is what you get, this is what you see. And this is also what limits or defines the size of your network all in all, the size of the cluster. The next level of evolution came in the form of a layer 3. The previous 2 examples, you had a clear layer 2 domain, the entire network. It's good from one thing, clarity, simplicity, visibility, everybody knows everybody. Layer 2 is nice, it's simple. Also from the bad thing, large broadcast domain, some ways to protect against that, but still, it's not the greatest thing in the world, but in a way of having 2 switches and everything underneath, it was better, it was more plus than minus. The rightmost example kind of breaks these paradigms and says, I want a top-of-rack device connecting to servers, that's my layer 2 domain. Each such rack is going to be a layer 2 pod, and from that point upwards is going to be a layer 3 domain. Now, layer 3 has its own attributes. It's working. It's been working for the last 20 years. It's what runs the internet. So we're pretty much safe on running with layer 3. We're pretty confident on that. The thing is that within that layer 2 network, we needed to have the ability to still identify or recognize layer 2 elements from different layer 2 islands. And this is where overlay came into play. So we needed to have all sorts of tunnels that interconnect between these layer 2 islands. Now, these tunnels could be starting up at the top of rack itself, where the layer 3 domain opens up. And this is where I will open my termination endpoint for the tunnel, also known as VTEP. Another option would be to open that tunnel still on the server. Now, why should I have this option versus the other? I'm not in the business of promoting one solution on top of the other. Both solutions are valid, both solutions work, and both solutions are needed. In some cases, both are mandated. All right? So it's not about what is better, this one or the other, but how to utilize both of them and why do we actually need both options. When going into kind of a VXLAN domain, kind of extending again the VLAN domain, there are two options in general, two options. One is with using a controller, and other is without using a controller. Pretty simple. What you see here is an example of running, let's say, either OpenStack or NSX termination endpoints. One sec, where is the laser on this? This one. So termination endpoint can be here, again, at the server level. It can be here at the top of rack, and then the tunnel can be between switches or from a server to a switch or between two servers. Essentially, you want to connect between layer 2 domain via a layer 3 network. So within other controllers, OpenStack is an option. NSX from VMware, there are more options here. That's the controller-based option. And then in parallel to that, there is the controller-less option. Why should I go with a controller-less option rather than a controller option? Preference. There's no essential good in that, and there's no essential bad in the other. Both are valid, and both work, and both are deployed, and we have lots of examples that we can show with either option. If you're not in the business of putting all of your eggs in one basket being a controller, then you go with a control plane protocol, the likes of EVPN. EVPN based on BGP, we're going to touch that in a minute. So again, controller, controller-less, both are working. A brief about portfolio, because I'm coming from a vendor company, just to kind of recap of what's available. I'm going to use my portfolio just to show what's available. So from the Mellanox perspective, we're in the business of building chips, silicon chips. One option is silicon chips that we use to manufacture network interface cards, 10 gig and up, all the way up to 100 and 200 is coming soon. A lot of capacity, a lot of performance, a lot of capabilities, put that aside. That's the Mellanox pitch. But essentially, the network interface cards come to relieve burden from the CPU in order for the CPU to be totally focused or mostly focused on doing what CPUs are supposed to do, compute, right? So that's why the network interface cards in general exist. The switch side of things, again, starting from a silicon level, and then I've been having discussions with a lot of people in the industry, and one thing that comes, from start to finish, whenever I talk to people who build data centers, is one very classic truth. They need the network to be transparent and visible, as invisible as possible. We don't want to touch it. We don't want to feel it. We don't want to feel that it exists. What we want is the fact that all servers are connected back to everybody, to like a full mesh of everything, and the network seems to be completely transparent. Obviously, this is easily stated, but very, very hard to implement. So going back to portfolio-wise, we created our own silicon, what we call Spectrum, and on top of that, we built our own systems. One point to comment. We do build our own systems. We do build our own network interface cards with our silicon. We also push our silicon out so other vendors can build themselves, right? It's not a sole proprietary type of an implementation. And then on top of that, not always it's easy to implement or to utilize these capabilities from the software or from the system. So we also had some software on top. Software can be such that accelerates performance of the silicon, such that enables user experience, which is more common or more comfortable for the end user to utilize. So in a nutshell, starting from silicon and all the way up to software to make things a bit more visible and performance ready, and then from top end to end, from a PCI interface towards a CPU to another PCI, the entire portfolio can be based on, say, silicon or Mellanox devices. One point to comment, this is fully interoperable with any other vendor, right? Any item here as a standalone is a standalone item. You can use that and connect to everything else. Some people in the audience here have already tried that, I know. So yeah, it's working, it's easy, it's all standard. Ethernet exists for 40 years. Easy and relaxed. So putting the portfolio aside. Now, why is VXLAN overlay such a challenge? I was commenting about the interface card, the network interface card, that its sole purpose is to relieve items out of the CPU. If the CPU needs to handle the interconnect all day long, and this interconnect is 100 gig, then the CPU only does I/O. It doesn't do computation. And then you have a large server, which you pay $10,000 for, and you're not utilizing it to 10% because it's only doing I/O. So what you want is for the interface card to offload as much as possible from the CPU. The few, or the most demanding things, demanding items that are being offloaded from the CPU is the examination of the packets as they are coming in or going out. Checking of the checksum for the packet, for example, is a trivial item, and this reduces large percentage of the CPU overhead. Now, the thing is that the VXLAN header kind of breaks this paradigm. How does it do it? The VXLAN header by itself is a UDP packet. Going into a server, the server looks into it. All of the offloads, the trivial inherent offloads on the NICs are TCP-oriented. So they look at this packet, they don't really know what to do with the UDP. So what do? They push it up to the stack. Going up to the software, now the CPU needs to handle it. CPU needs to handle it means the CPU utilization is dropping. Again, on the compute side of things. So what you want is for your interconnect to leave the CPU aside and let it do computation while taking care of all of the I/O. This is where the implementation of the VXLAN on the network interface card comes into play. Two levels here. First is just to look at the packet, understand what's inside, run the checksum, make sure it's a valid and functional packet, and only then take it up to the application if needed, or reroute it if needed. But take care of it, and again, relieve the CPU. That's tier 1. Tier 2, take the packet and open it up. It's a tunnel. There's a VXLAN header. Take it out. Look at the inside of the packet. Look at the VLAN. And then decide, based on the input or the inside of the packet, what do you want to do with it. So again, 2 tiers. 1, being aware of the VXLAN, and 2, encapsulate or decapsulate the VXLAN. These are the benefits that you can expect from a network interface card, and this is the challenge that VXLAN is promoting. A small example, this is based on kind of an older equipment that we have. That's why the numbers are talking about 40 gig, but essentially the numbers reflect themselves with a 100 gig interface as well. What you see on the left side is just physical throughput, no tunneling at all. This is where, as I said earlier on, the network interface card, the traditional one, take care of all of the overheads of the TCP/IP stack, right? So this is how you get to close to 90 plus, 95% utilization on the physical layer. And then you add the VXLAN. VXLAN without offloads drops the throughput from 37 gig to 17, more than 50% drop. What happened then? The CPU is fully utilizing on the I/O side of things. You look at the CPU utilization there. It jumps, right? And this spike of the CPU, first off, reduces the bandwidth, and second off, reduces the capacity of the CPU to do actual compute. And then the column on the right kind of brings back the VXLAN offload capabilities on the network interface card, and then you see the graph coming back up. It's almost on par. Still, there's always some percentage of overhead, but it's almost on par like what you will have on a bare metal server. Some network interface card will show better performance here, some less, but it's going to be in the same ballpark, be it Mellanox or other. It's going to be in the same ballpark. So, but the concept of having this offload capability is somewhat mandatory. Some examples of how this is done. I'm not going to delve into the actual details on this, mainly because we are in the capacity of time. And if you have more questions, you will be able to find me upstairs in the booth. Essentially, very trivial. The entire idea here, and being something which is implemented, say, via OpenStack, which is not a trivial environment to play in. You want something which is in-box, as simple as possible to utilize. So you have this community link here from Mellanox. There are like 2-3 simple commands inside. You run these, and you have the network interface cards operational as a VXLAN offload device. Again, pretty simple. I'm going to skip that. This is kind of an example of what I was showing before, in the sense of offloading stuff from the CPU. These 3 devices, an example of what can be created out of the Mellanox silicon. You will see these devices in the form factor of Mellanox or in the form factor of other switch vendors. Essentially, these form factors exist all over the place, not unique. What is unique is this form factor, which is a bit special, 16 ports of 100 gig in a very small device. You can see the device, again, upstairs, so please do come to take a look. Now, we've been talking about the overlay, and we've been talking about the cloud and how to utilize and implement this. What is Open Ethernet? So Open Ethernet is a concept. The sense is that up until today, up until a few years ago, the only option that you had was to buy kind of a monolithic system. It had the silicon inside, the enclosure by itself, and the operating system on top. Let's call it iOS, right? Everything was grouped in one chassis, and you could not do anything about it. You could not put your foot in, you could not break anything. It was what you got from the vendor was it. And then Mellanox, as well as a few other companies, small companies, let's say Google, Microsoft, smaller companies, came into play and said, okay, we're going to break this paradigm, and we're going to say hardware is a standalone, software is a standalone, and now let the games begin. Mellanox came into this, again, as a hardware vendor. So what we have seen before on the systems, it's bare metal systems. I can offer you these systems with my operating system, Mellanox OS, and you can say, no, it's a lock-in. Again, you're locking me to use your equipment. Fine. So don't use Mellanox OS. So just take the system. You can develop your own operating system. You can take Mellanox OS from me. You can take Cumulus Linux from Cumulus. I can offer it from myself as well, but you can get it directly from Cumulus. You can take the Microsoft Sonic implementation, which is open source. Run this on the switch. You can take other open sources. You can take SnapRoute, which is another one. You can take OpenSwitch, which is another one. Your choice. I'll give you even further than that. You can take native Linux and run it on the switch with an internal driver that we worked to push upstream the Linux kernel. You can take Ubuntu, run it on these switches, and you have every capability that you want to have on the switch working on the hardware level performance. So that's what Open Ethernet is all about. SwitchDev is the name of our Linux driver, right? Cumulus, Mellanox OS, OpenSwitch, SnapRoute, Quagga, Metaswitch, Microsoft, all of these are available and enabled. So this is what Open Ethernet is all about. You get the hardware. By the way, you don't want the hardware for Mellanox? Go get it from an ODM. This is not my box. It's just my silicon inside. This concept exists not only for Mellanox. You can go to Acton and Quanta or the likes and buy a system which is essentially open. That's the paradigm shift that happened in the industry. This is what weakens the giants such as Juniper, Cisco, that likes. All right, so how does the OpenStack item comes into play? A Neutron plugin, which is implemented into OpenStack, enables the OpenStack to see, so to speak, the switch and run the configurations within the switch, VLAN and so on. Just running through, again, NSX as we have discussed before, and that's the option of the EVPN. What does the EVPN give you? Essentially, you work the underlay. That's the basic BGP that everybody can implement, or a very traditional BGP, and then you start to work the overlay. And then the overlay is, again, you establish after the fact that you have all of your topology in place, and this is what the controller used to do. Now, BGP as a protocol does that instead, right? And then you can run on this infrastructure and establish your tunnels within the boundaries of the tunnels that you have, of the underlay that you have. In the specifics, I'm just going to run through the details here. basically because lacking time, and I'm not going to be able to explain it well in a few seconds, but again, you can ask around. Essentially, you come to the point where you want to open up your EVPN. Now, it's sometimes perceived as something very complicated. From the implementation point of view, it is very complicated. From the user point of view, a lot of command lines that establish everything, but this essentially is what you need. These two lines that enable the EVPN. After the BGP is in place, that's all you need. These two lines open up the EVPN. It's that simple. These commands come from the Cumulus Linux CLI. Right? EVPN is not implemented in Mellanox OS, for example. So if that's the approach, you will go with a Cumulus Linux. All right, yeah. Another approach here, how to cope with broadcast, onion unicast, and multicast traffic, still inherent within the boundaries of the well-known types of traffic. And this is where scale, I would say, comes into play. Again, this is very specific to the Spectrum device with the ability to run or to map more, say, VXLAN or VNIs to VLANs and vice versa. This is what eventually establishes the size of the data center that you have. And the first picture that we saw, we talked about the fact that layer 2 is kind of inhabiting the top of rack and down, and layer 3 is inhabiting the upper layers. And this kind of takes you through or to the next level in terms of scalability. But where does scalability stop? It stops here. On the amount of VNIs that you can map from one top of rack, it needs to see all of the other top of racks because they are in a different layer 2 domain. So it needs to see all of the other layer 2 domains. That's now the scale factor of your network. And this is where the Spectrum silicon provides better approach. I'm going to skip through that. I want to show you an example. Yeah, I'm going to skip through VXLAN symmetrical routing and asymmetrical routing. Again, something that puts us in a better light, but I'm going to skip it. I mentioned software. Neo is a software that is promoted by Mellanox, developed by Mellanox, and supports a variety of operating systems. It's not just for Mellanox equipment, and it doesn't cost. It's not a full-blown VXLAN controller. Don't get confused. It can integrate into a controller, but it's not the controller by itself. It does give you a lot of insight into the switches and the ability to configure these switches, but not only switches, also the interface cards. So Neo can give you kind of a holistic approach or holistic view on the entire implementation. Lots of insights, lots of goodies within that. And then, yeah, that's the example. I'm not sure if we have anybody from Sys11 here, but this is exactly what they have been doing. They have been implementing VXLAN on the network interface card, in some cases on the top of rack. Why did they do both? Because some cases they just needed. They had a bare metal server that was just there and they needed to utilize it, so whatever was connected to that needed the VXLAN function. It's not that you want to do VXLAN on the switch, you just need to do VXLAN on the switch. And while having equipment that enables you, even in the future, even if not now, but enables you in the future to utilize all of these functionalities, you save yourself in terms of a future-proof type of solution. I'm going to stop here, and then I want to hear from you guys if any questions arise. Sure.
We don't have time for questions.
Let's take one question. Let's make one question.
So, the question, if I buy the hardware from Mellanox, but I would like to install some other software, like from Cumulus Networks, then how does the support work?
We provide support specifically for Cumulus. If you will go and swap the software that you have with Sonic, for example, which is an open source, then it's open source. Nobody gives it support. It's yours. If it's something that we can help you with, we will help you. But if it's Cumulus, we provide support. If it's Mellanox OS, we provide support. If it's something which is more specific to another vendor, you will go to that vendor, be it Mellanox, be it SnapRoute, be it somebody else.
Okay, so there's a risk between pushing, in case if something is not working, then I think my vendor from the software
Specifically, if you will go with a Cumulus solution, then you're safe. If you will go with a Sonic solution, then you're safe. Specifically because we are working very closely with Microsoft, and we are the one who, well, in a way, developed a lot of Sonic. Other OSs, give me a call. Give me a call and ask me before you do anything. Yeah. All right? Guys, thank you very much. Sorry for being so fast, but you know, time is running too fast here.